Okay, so this is a very good example, which to my mind really kind of shows you um, why this might be useful for your engineering, and it's inspired by a real life example. So there's some kind of a concrete dome. Now, I don't know what I saw this in a talk. It's some kind of concrete. I don't know what it's for. But you can imagine why something might be constructed. And it was already made, um, but because other structures were going to rely on it, they needed to be sure about the strength of it, the strength of the concrete, and therefore the strength of the structure overall. So what they did is they took 50 small samples, so they basically bored holes in it to see how strong the concrete was. So they took, now the numbers are made up. So they took 50 small sample bores. So bores is I was just at samples. Bores I think is a word you would understand. The sample had a mean of 21.4 megapascals. So of the 50, so there's 50, they calculate the strength of them, find the average of those, 21.4, and a sample standard deviation of 3.9. What that means is most of them are kind of like, let's call this 21, let's call this 4. Most of them are kind of between 17 and 25, but some of them are a bit stronger, some of them are a bit weaker. The structural engineer determined that at least 60% of the concrete would have to have a strength of more than 20 megapascals. So what they're looking at here is they don't want to say, oh, I want, it's not that, okay, if the average concrete strength is 20, I'm happy with it. This is going a little bit further. They want 60% of the concrete to be stronger than 20. So it's a slightly different thing. Okay. So first question is find a 95% confidence interval for the population mean, and this is just some notation. So the small number, the lower bound where we think is probably the weakest it is, and the strongest it is. So we'll use this formula here. So x bar is here, it's 50. We'll go back to t. Sigma is approximately the standard deviation is 3.9. N is the sample size is 50. And I think I said x bar is 50, maybe I'm getting a bit tired. X bar is 21.4, the sample mean. We need to find t. So here we have 95% confidence and n equal to 50. So really we should go to n minus 1, which is 49, but it's not there. And if it's 95%, it's 5% in the tails. It's this 2.009 number. So we're getting x bar, which is 21.4, plus or minus is 2.009 times population standard deviation, which is estimated as sample standard deviation 3.9, divided by square root of 50. And so we're going to be 95% confident that the average of all of the concrete is in the following. So let's calculate some numbers. And this, that we have a sample size of 50, should make this quite a tight thing. Although the standard deviation is quite big, so we couldn't do it perfectly. So 21.4 minus 2.009 by 3.9 divided by root 50, and getting 20.29. And then the other one, I'm just going to change that minus to a plus. 22.51. So we're saying that the average strength of the concrete across the entire dome, if now the sample bores have to be taken at random, is between these two numbers. Okay. This is kind of an upper estimate of how strong it is. So that's kind of quite optimistic. More conservative is more like 20.29. Okay. Question 2. Assuming that the population mean is equal to the sample mean, so this is assuming that mu is actually equal to 21.4, which is a ballsy kind of an assumption. Like, you probably should be a bit more conservative and assume that it's only 20.29. And the compressive strength normally distributed, so we're assuming that the concrete, the strength of it is actually normally distributed. Find the characteristic compressive strength, okay, the strength S such that only 5% of the concrete has a compressive strength of less than this. So this is kind of saying this characteristic thing is kind of really, it's a measure of, look, pretty much 95% of the concrete is stronger than this. So we will draw a picture here to help us understand what's going on. Now maybe we will say let X be the compressive strength. So let X be the compressive strength. I'm just going to write strength. And we're assuming that it's normally distributed with an average equal to the sample mean, so 21.4, and a standard deviation equal to the sample standard deviation, which is 3.9. Okay, let's draw a picture. This is going back to the previous section. So the average is 21.4. We're trying to find the value S such that, what does it say? Only 5% of the concrete has a compressive strength less than this. So we're looking for a value of S such that there's 5% in here. So as ever, with a normally distributed problem like this, we convert it into a Z problem. So to convert it into a Z problem, and I could have left more space for myself here but didn't, we draw a Z curve. Now rather than talking about S, which is an X, let's talk about a Z1, such that there's 5% in here. Now I don't really have much space here, but if you have done perhaps some exercises on the normal distribution, you'll be used to this. So by symmetry, now let me call this minus Z1. Okay. So if I go to plus Z1, by symmetry, there's also going to be 5% in here. And therefore, there's 95% in the long left tail of plus Z1. So what I have to do is I have to find the value of Z such that there's 95% in the long left tail. And that's this Z thing. So I have to find the Z value, which is 95% here. So we go back here and we got these two numbers. So I have a choice between 2.57 and 2.58. They're both, actually that's absolute nonsense, isn't it? Because it's 95%, excuse me. So 95%, where is it? So there's a choice of 2. I got 1.64 and 1.65. Now you can take 1.645. That's probably the cleverest, isn't it? But I'm happy with either. I'm going to take 1.645. So the Z1 is 1.645. So if you're stuck, pause it, slow me down, whatever. Well, you can't slow me down. You can only pause me and figure this out. So we're looking for a strength such that only 5% of the concrete is weaker. Convert that into a Z thing. We'll call it a minus Z1 because the peak goes to 0, so this is a negative number. So this S in this picture is a minus Z1. We're looking for 5% in there, 5% in the short left tail. Turn it by symmetry into 5% in the short right tail of a plus Z1. So that's 95% in the long left tail. What is in here but long left tails? And we found 95%. Well, we split the difference, 1.645. So now we're going to convert back. The X value, which is S, is equal to the average, which is 21.4, plus the appropriate Z, which is minus 1.645, times the standard deviation, which is 3.9, and this is megapascals. .98. So 95% of the concrete is estimated to be stronger than this. But that's actually interesting because it's not if we use 20.29, it would have been even smaller. But look, we'll just go to the thing. So if there's parts of the, so if there's a thing where, I shouldn't talk here because I'm not an engineer. Okay, so let's look at the third question. So assuming a population of mu1, now mu1 is the conservative estimate, the 20.29. I'm going to write that down. So assuming 20.29, so assuming the conservative estimate for the population mean, the lower of the confidence interval, the population standard deviation equal to the sample standard deviation, so that's still 3.9. And the compressive strength normally distributed, so again we can go with x being normally distributed, but this time we're being a bit more conservative. What proportion of the concrete has a strength of less than 20? Okay. Okay, let's go. So we'll draw a picture again. So this is a different normal distribution, so we're using a more conservative figure. So we're taking 20.29 as the average, and we're looking at what percentage of the concrete, if the concrete strength is normally distributed, is weaker than 20 megapascals. As usual, we're looking for this area, so we turn it into a Z picture. And because it's to the left, it's going to be a negative thing. I'm going to call it minus Z1, or we'll call it minus Z2, which we will find in a moment using the transform, and we're looking for this area here. Okay, so let's find this, well, I'm just going to call it Z2 now. Yeah. So Z2, using the formula from the previous section, is the X value, which is 20, minus the mean, which is 20.29, divided by 3.9, and we can only go to two decimal places here, so that's all we'll do. 20 minus 20.29 divided by 3.9, so I get minus 0.07. Okay, now we're interested in this area. This is the answer. This is the proportion. I was going to write proportion of concrete that's weaker than 20 megapascals. It's the same as this number here, and we have to get this short left tail. Now remember, by symmetry, the short left tail of minus 0.07 is equal to the short right tail, and I think I have space to draw the picture. It's equal to this. And what we should do here is find the total area minus, and I haven't drawn this every time in the previous section, so there's no harm seeing it, the long left tail of 0.07. And that we're going to get off the table. So the proportion of the concrete that's weaker than 20 megapascals is 1 minus the long left tail of 0.007. So it goes 0, 0.07, we get 5279. So let me slow that down. So the Z value is 0.07, so 0.07.5279. So I get 1 minus 0.5279. So I'm getting 47%. Right, and now, so 47% of it is weaker than 20. Okay. Now the question is, will the structural engineer be happy with the dome? I should write down the solution here. well, what does a structural engineer? She wanted at least 60% of the concrete to be stronger than this. At least 60. But there's 40%, 7% of it is weaker. So only, that's not equal to 47%, it's 47.21. Maybe I should be a bit more careful. 0.4721, that's approximately 47%. That kind of approximation is okay here because it's all rough anyway. So if there's 47% of it is weaker, only 53% of it is stronger. And so she's not happy. Wanted more than 60% stronger. And you can see, like, she's been quite conservative, really, because she probably could have maybe used 21.4, in which case it would have turned out, it would have been fine. But, I mean, the concrete is still the same, and maybe you're better off being careful and using 20.29. Now, that's only, like, there's still a 5% chance that it's less than that. And, you know, like, if the calculation was really strong about you really need 60% of this to be strong, then, I mean, you probably really should be running with a 99% confidence interval. So there's only a 1% or a 0.5% chance that something might go wrong. And all this kind of uncertainty is where your factors of safety and factors of ignorance come in. Okay. So a similar question to this is autumn 2020, and I might have something like one of these on the assignment. I'm not sure yet.